In chapter 4, we're going to really switch gears here from the two previous chapters and talk about antiderivatives and the process of integration. Okay, so once we finished up chapter 3, we really wrapped up what is called differential calculus. We're going to kind of mark an end to that subject, but we'll still see it, from time to time. But officially starting now, we're going to start a new section of calculus called integral calculus. So up until this point, you guys have been given functions and been asked to find their derivatives. So you can see in this little table the derivative of x squared is 2x, and so on and so forth. That's what we did in chapters 2 and 3, which again is called differential calculus. We took derivatives and we learned all those processes and concepts. So we got some new notation, and of course we all remember that when we write f prime, we say f prime of x is the derivative of f of x. Well, if you were maybe wondering if there was a way we could maybe start with the derivative and work backwards to figure out what the original function was, the answer would have been yes. Integration is the process or the operation that reverses differentiation. So starting in this chapter, we're going to be seeing derivatives as our starting point, and we're going to try to work backwards to figure out what original function gave us that derivative. When we go through that process, that is called integral calculus. So with this new idea comes some new vocabulary, and that is to say, when we're trying to find the original function f of x, we call that the antiderivative of f prime of x. So whenever you see this word antiderivative, just kind of think of it as the original function. Of course, you'll never really ever see it called the original function, but anytime you see that word antiderivative, we're really just talking about the function that gave you a derivative. So now that we're starting this new portion of calculus, there's a bunch of new notation and vocabulary that we're all going to have to be okay with, and the first is what we're going to see a lot in this chapter and from here on out in this course, and it's this notation that you see right here. So why do we use this weird symbol to show integration? Well, that we'll get to in 4.3, but for now you just need to realize that when you see this expression, it's instructing you to find the antiderivative of f of x, and then this little dx is telling you to do that with respect to x. So the function that's always sitting right here, this f of x function, be careful, it's actually not your original function. The function that's always there is a derivative, and the reason we know that's a derivative is again because this expression is instructing us to find the antiderivative of f of x. So be careful, it's really easy to get confused with an f of x that's an original function and an f of x that's sitting inside this symbol right here, which again is telling you to find an antiderivative. And we'll go through all those steps and processes, but we just want to get a good idea and familiarity with some of these notations. So if I were to write this symbol, f of x dx, and I told you that was equal to big F, we would know that big F is the antiderivative, or again, the original function of f of x. So again, gotta be careful with these new notations. Big F is the original function, or the antiderivative, of little f. So what would it mean if we took the derivative of big F? Well, if we took the derivative of big F, that would get us back to f of x. The derivative of big F is little f. So you can see as soon as we kind of reverse things that we've gotten so familiar with, it can kind of feel a little confusing. So please go over this little idea here, because as soon as you kind of get lost with this notation, these problems are not going to make too much sense to you. So what is this process, or what is this thing called? Well, this thing is called an indefinite integral. This process of integral calculus is called an indefinite integral. So what do we have here? Well, that weird symbol, which we'll talk about in 4.3, or I'll give you a better reason why we use this symbol in 4.3, is called an integral sign. The function on the inside of that integral sign, or a derivative, remember this function right here is a derivative, we call the integrand, and then that dx is just the variable of integration. What letter are we integrating with respect to? Okay, so the good news about integration is we're not going to learn the long way of doing it like we did with differentiation. We're going to just jump straight to something called the power rule for integration, and it's going to feel a little bit like the power rule for differentiation, but of course it can't be the same since we're undoing a derivative here. So the first thing you should realize is that when we talked about taking a derivative back in chapter 2, I refer to something called derivative friendly, which if you recall is a number, an x, and then a power. That still applies here for the power rule of integration. You'll notice the form needs to be a number, and I guess there's an invisible 1 here, an x, and then a power. If your problem looks like that, or if you can manipulate it to look like that, then we can apply this power rule for integration. And it's a fairly simple process. All we do is we take the power and add 1 to it, and then divide that x to that new power divided by that new power. At the end here, we're going to add this plus c, which I'll talk about why it's there, but just so you know, that's called a constant of integration. One little trick question, I suppose, could come up if you're not too careful, and that is this. If you ever see a power of -1, we can't do that problem, not at least yet. The reason, of course, is if it was a -1 power and we added 1, we would get 0, and of course we cannot divide by 0. So, not too bad. The power rule for integration is fairly straightforward, just like the power rule for differentiation. Just a little recap of the steps you'll do here. If you ever want to integrate a plane x, and that's the key, it's got to be plane, we can't see stuff to a power, then all we need to do is add 1 to the power, divide by the new power, and add a plus c, or add c to the end of that. So let's go ahead and try this little power rule of integration. We're going to have a bunch of rules in the next slide that you're going to see, and one of those rules that I'm going to use right here real quick is to pull that constant of 2 out to the front. But I guess before we do that, we need to realize what this notation is asking us to do. We're being asked to find an antiderivative of 2x. The reason we know we're being asked to find the antiderivative is because of that integral symbol, which means 2x is a derivative, and we want to find the original function that gave us the derivative of 2x. Okay, so that rule I was talking about will allow us to pull constants out to the front of the integral sign. And one little warning that you're going to have to keep in mind is we can only pull out constants and not variables. So now that we've pulled the constant out to the front of that integral sign, you'll notice our problem now looks like the power rule for integration. We have an x to a power, and if we follow this power rule for integration, we're going to add 1 to the power, which is 2, and divide by that new power, which is again 2. And then don't forget that plus c at the end. We should of course simplify this, and those 2's will cancel, and we'll get x squared plus c. I guess to be a little thorough here, I'll go ahead and put y equals on this side, just so you can see that that's the original equation that gave us the derivative of 2x. That is what we call a general solution. It's the solution where we don't know the value of c. And you'll notice real quick, if I asked you to find the value of c, you would need to be given an x value and a y value so you could find that c. But we're not given any extra information, so all we're going to do is call that a general solution since we don't know the value of c. So now let's talk about why there is a plus c and why you're always going to have to remember to put a plus c when you find an antiderivative or when you take an integral. And the best way I can get you to see that is maybe visually here. Let's pretend I knew that c was 0. We don't know it's 0, but let's pretend we knew it was 0. Let's also pretend we knew c was 1 in a different scenario. And answer this question. Are the slopes different for the same values of x? Well, if we think about this, if we wanted to find the slope at a point for x squared plus 0, we'd take the derivative, which is 2x. If we wanted to find the slope for the graph of x squared plus 1, we would take the derivative, which is still 2x. So if I wanted to find the slope at 1, as you can see in this picture, I would plug in the 1, which would be 2 times 1, which is 2. For the x squared plus 1, I would plug in, again, 1 in the derivative for x squared plus 0, which would again be 2, and we get the same exact slope. The slopes are exactly the same, and that's kind of the key. We don't know exactly what that c was. You'll notice, and I'm going to kind of list off a bunch of possible scenarios, but what if c was negative 2? That derivative would still be 2x. What if c was negative 1? That derivative would still be 2x. If c was positive 1, positive 2, even if c was the value of pi, all those derivatives would still be 2x, because the derivative of a constant is just 0. So that's why we need to put that plus c at the end of every antiderivative we find. We don't know what that constant was, if there even was a constant. So we have to put that plus c to kind of take the place of a constant that we don't know. When we know the value of c, and again, if you refer to something I just said a moment ago, I would just need to give you an x and a y value so you could plug that in and find it. But if you know the value of c, we call that a particular solution. So the thing you're going to have to take away from this slide is that a function has an infinite number of antiderivatives. Okay, on this slide, it's a great little reference slide for you to have. On the left side of this slide, we have all the derivative rules we studied, so a lot of those should look nice and familiar. And then on the right side, we have all the corresponding integral rules that we need to know. And this line that you see here dividing the table is going to kind of be the dividing line of where above the line, you should definitely have those memorized. But below the line, we'll use those from time to time, and maybe they aren't the most pressing thing to have memorized. But definitely above this line, make note that you should know all of those by memory. So let's go over a couple of these real quick. That constant rule is when we integrate a constant with respect to x. When we integrate a constant with respect to x, we get that constant times x plus c. So be careful. We know the derivative of a constant was 0. But when we integrate a constant, it becomes kx plus c. This was the rule, the constant multiple rule that I used in the last slide, where you can take constants multiplied by functions and pull them out to the front of the integral. The good news is, just like with derivatives, if you're adding or subtracting functions to each other, you can integrate those just like taking derivatives separately. You can integrate f and integrate g separately, and then add or subtract depending on what the signs are. You just saw the power rule in the last slide, so that's a little reminder there. And then our two basic trig integrals. Just like the derivatives, you're going to have these two basic trig integrals memorized. The integral of cosine is positive sine, so be very careful. The integral of sine is negative cosine. And again, please don't forget those plus c's. It's usually the one thing that'll get you into some trouble, I suppose, because it's easy to forget to put that plus c. Okay, let's try a bunch of examples and try to figure out how to find antiderivatives, or take an integral. So we're trying to evaluate the integral of 5x cubed dx. So one more time I can kind of remind you of this. That 5x cubed is a derivative, and this expression is asking us to find the antiderivative, or the original function. So we can use that constant multiple rule that allows us to pull the constant out to the front. And now we can apply the power rule to this problem. We're going to add 1 to the power and divide by that new power, and again, don't forget that plus c. To make this look a little more simplified, since we usually like having a number, an x, and a power, we can take the 5 and the 4 and write that as a fraction, so this would become 5 over 4 times x to the 4th plus c. Keep in mind, we have to keep that plus c there because we don't know what that number could have been. something to kind of realize, even though I don't think a lot of you will actually do this when you're doing problems, is you can always check your work. How do we actually know if we found the correct antiderivative? Well, we could take the derivative and it should get us back to the original problem of 5x cubed. So just a quick little check of our work. If we take the derivative of our answer, do we get 5x cubed? Well, this plus c, that's a constant. The derivative of a constant would be 0. The derivative of 5 over 4x to the fourth would be 5x cubed. And of course, that gets us back to the original problem. And we've kind of verified our answer. Okay, here we're being asked to take the integral of several functions being added or subtracted, which again means we can use the sum difference rule, which just is a fancy way, I guess, of saying we can integrate each of these functions separately. And since we're integrating each of these separately, we can apply the power rule to each of these. They fall into the category of being integral friendly, a number, an x, and a power. So when we apply the power rule to 6x squared, it becomes 6x cubed divided by 3. When we apply the power rule to 4x, it becomes 4x squared over 2. And when we take the integral or find the antiderivative of 1, you've got to be careful here. It's not 0. When you find the integral of a constant, it's the constant times x. So it will be 1x, and then again, don't forget that plus c at the end. I suppose we could leave that, of course, as the answer, but we can simplify it really quickly here. 6 over 3 would be 2, 4 over 2 would be 2, so we get a final answer of 2x cubed minus 2x plus x plus c. That is the original function, or the antiderivative, that gave us the derivative above in the original problem. Outside those two examples, all problems that you see probably will come down to one factor. Can you get your problem to look integral friendly? And that's the key. And I guess I can put that in quotes since that's my little way of saying a number, an x, and a power. So of course that's going to rely on a lot of your algebra skills. So let's try to make this a problem here integral friendly. Just like in chapter 2 when we're taking derivatives, we need to change square roots to powers. But before I do that here, I'm going to go ahead and use a little property of fractions that allows me to split this fraction into two fractions. Since we're dividing x plus 1 by one thing in the bottom, we can split this into two separate fractions. And again, like I was saying before, just like chapter 2, we don't want to keep that square root notation. We want to change that to a power. Now we can definitely simplify this. This x in the top of the first fraction has a power of 1. When we simplify this first fraction, we'll do the power of 1 times the power of a half, which is a positive half. If we want to take this x to the half in the bottom and move it to the top, we just have to take that power and make it a negative. And now we've achieved integral friendly, just like we thought of back in chapter 2, derivative friendly. We have a number, an x, and a power, and we can integrate these two things separately. So when we add 1 to 1/2, we'll get 3/2, and we'll divide by that new power, so divide by 3/2. When we add 1 to -1/2, that becomes +1/2, and then again we have to divide by that new power, which is a +1/2. And then don't forget the all-important plus c at the end. Usually you don't want to leave your answer in this form, especially when you're dividing your x by a fraction. So to get these fractions out of the bottom, hopefully remember, you just need to multiply by the reciprocal of that. So when we simplify this, the answer becomes 2 over 3 x to the 3/2 plus 2 over 1, or just 2 times x to the 1/2 plus c. Okay, in these next two examples, we're going to talk about finding that value of c. And remember, when we know the value of c in a solution, that's called a particular solution. So in this problem, we're being asked to find the particular solution of the derivative 2x minus 1 with the initial condition 1, 1. And again, remember, a particular solution is just the equation where we know know the value of c. So this is really just two steps. We need to find the general solution, which is the one where we don't know the value of the c, and then we can go to the next step and find that value of c. So let's go ahead and do the first step, and that is find the general solution. That means we have to find the integral, or the antiderivative, to this derivative. If you recall back in 3.8, at the very end of 3.8, we talked about something called a differential. And I said we wouldn't need to do that thing till 4.1. This is the problem where we need to use that little trick on, maybe it's not really much of a trick, but it's more of a form, so that we can get this to look the right way so we can find the antiderivative. So we need to change this derivative into its differential form. And if you recall, that just means multiplying the dx to the other side. Once you do that, then we can integrate both sides of this equation. And of course, like we've known for many, many years, if we do something on one side, we have to do it to the other. So we'll integrate the left side and we'll integrate the right side. Okay, on the left side, I guess if you want to write this in, there's an invisible 1 here, even though we don't have to write it, but we're trying to find the integral of 1 with respect to y, which is why that dy is there. Well, keep in mind, the integral of 1 with respect to x would have just been x, like you saw on the last slide. So of course, the integral of 1 with respect to y would just be y. When we integrate the right side, luckily those two functions are very basic. The integral of 2x would be 2 times x squared over 2. We added 1 to the power and divided by that new power. And then the integral of that 1 with respect to x, though on this side, would just be x. And then of course we can't forget that plus c. Just simplifying this a little bit, of course those 2's would cancel, and we'd end up with the equation y equals x squared minus x plus c. That is the original function that gave us the derivative of 2x minus 1. But we don't know what that plus c was. So to find that plus c, we have to kind of keep in mind that there were actually an infinite amount of answers. We have all of these graphs here that I'm drawing, and of course there's an infinite amount more. But we're just trying to figure out which c did we have in the original problem that gave us the derivative of 2x minus 1. So you can see a bunch of c values here, and let's see which one was really the correct one. So in step 2, we have to use the known point. An initial condition is just a, I guess, more complicated way of saying it's our known point. So of course this is our x and this is our y, so we can take those two values and just plug them in. When you do the math, we'll find that c was equal to 1, so the original function, or the antiderivative, or in this case the particular solution, is x squared minus x plus 1, which means it was this parabola right here. It's the parabola that goes through the point 1, 1, or in other words, a c value of 1. This next example is identical to the last example, but presented in a different manner, which I think can throw some of you guys off, so I definitely want to cover this form of just the problem we did before. Here we're solving a differential equation. So what does that mean? Well, that's just really a different way of saying find a particular solution. When you're being asked to solve this differential equation, that's just another way of asking us to find a particular solution. So luckily, it's the same two steps that you saw from before. We need to first find the general solution, which is where we don't know the value of c, and then we can take the point they give us and plug it in. So the first thing we need to do is, unlike the last example, f prime of x, we don't want to have written that way. We know another way to write f prime of x is dy dx. The reason we want to write it this way for this problem is it's more helpful to us because we want to change that to a differential form, which again would mean to move that dx to the other side. Once we do that, we're ready to go. We can integrate both sides of this equation. Just like the last slide, the integral of 1 dy is just y. And then on the right side, two nice and simple integrals to take. They're integral friendly, so we're going to add 1 to the power of 3, so we'll get x to the 4th over 4. We still have the 8 in front of that. And then the integral of 5, be careful, it's not 0. We're not taking a derivative here. It would be 5x plus c. Again, we should definitely simplify this to get a general solution of 2x to the 4th plus 5x plus c. The last step is to find that c value. The only way to find that c is to take a point and plug it in to find the c. So of course, up here we have our point written function notation, so hopefully you're still okay with that. Our x is 1, our y is -4, so we're going to just plug that in. We have the point 1 comma -4, so when we plug those values in and do the math, we'll find that c is equal to -11. So what was the equation that gave us the derivative of 8x cubed plus 5? The particular solution, or the original equation, the antiderivative, was 2x to the 4th plus 5x minus 11. Okay, on this last slide, we're hopefully going to address some of the little ways that you're going to have to approach problems so you can get them to be integral friendly. Before you begin a problem, the most important step is to rewrite your integrand in a form that fits one of those basic integration rules, or in other words, integral friendly. So let's take a look at a few examples. Here we have 2 sine x plus 3 cosine x. That plus is the key. That plus lets us take the integral of both of those things separately. And then within that, since there's a 2 in front of sine, we can pull that to the front of the integral sign. Since there's a 3 in front of the cosine, we can pull that to the front of that integral sign. And we're kind of done after that. It's definitely integral friendly in the sense that it's a plane x in sine and it's a plane x in cosine. So if you refer back to that table with all the integrals that you're going to have to know, the integral of sine is negative cosine. The integral of cosine is positive sine. And then don't forget that plus c at the end. Theoretically, at this step, you could circle it and kind of finalize that answer, but just like you saw back in chapter 2, if you ever end up with a negative here with this negative cosine, it's really best to pull that out to the front just so you don't avoid any errors in the way you write your final answer. So if you pull that negative to the front, you'll end up with -2 cosine x plus 3 sine x, and then of course plus c. In this particular trig integral, looks a little complicated maybe, but if we use a little property of fractions here, we can maybe make it simpler. And that property is this. Since there's a cosine squared in the bottom of this fraction, we can split that cosine into cosine times cosine. If I do that, I can make two separate fractions. I can make a fraction where we take 1 divided by cosine, since there's an invisible 1 in front of the sign here. And then I can make another fraction as sine over cosine. If you recall back from pre-cal, 1 over cosine is secant, sine over cosine is tangent. So I suppose the question would be this: how did we know that this was the path to take? How did we know that we should simplify this to become secant x times tangent x? Well, the really only way I can answer that is going to be based on your familiarity with that table earlier in this PowerPoint. And that is to say, in that table, it turns out that we know the integral of secant x times tangent x. The integral of secant x tan x is secant x plus c. So I guess this just illustrates that you're going to have to become a little bit familiar with those integrals in that table, even though that line I drew on that table above that line were the ones you needed to have memorized. Below that line, you just need to know that those exist, and when you need them, just like in this case, you'll be able to use them. In this particular problem, we saw one like this with a square root from before, where we don't want to have a square root notation. That square root in the bottom can be rewritten as x to the 1/2. And of course, like we saw from our derivative days back in chapter 2, we can move that to the top with the 2 as a negative power. If you pull the 2 out to the front, we have something that can be found. We can take the integral of this using that power rule. We have a number, an x, and a power, so we can go ahead and apply the power rule. We'll add 1 to the power, which gives us a positive half, and then we'll divide by that new power. Again, technically, that is the final answer, but we should usually aim to simplify these things, and when we take that fraction and multiply by the reciprocal to the front, we'll end up with 2 over 1 times 2, which is 4, x to the 1/2 plus c. In this last example, just yet another reminder that we need to take those roots that we're going to see from time to time in problems and change them to powers. In this case, we'll change the cubic root to a 1/3 power, and since that x to the 1/3 power is outside of x minus 4, and there is no power on that parentheses, we can go ahead and take that and distribute to both of those terms. X to the 1/3 times x, we would add the powers. This is an invisible power of 1. So 1 plus 1/3 is 4/3. And then, of course, 4 times x to the 1/3 is just 4x to the 1/3. We have a minus between these two functions, which means we can integrate these two things separately. And since they're both integral friendly, all we need to do is apply that power rule. We'll add 1 to the 4/3 power, which is 7/3, divide by that new power. We'll add 1 to the 1/3 power, which is 4/3, and divide by that new power. Like you heard me say in the previous example, we could technically leave this as the final answer, but definitely we need to clean this up and make it look a little more simplified. So these fractions in the bottom are, to get them out of there, we're just going to multiply by the reciprocal. So 7/3 becomes 3/7, x to the 7/3. When we multiply 3 over 4 times 4, that gives us 3 x to the 4/3, and then again we have that plus c at the end. One of the easiest ways to kind of miss problems is to forget that plus c, so definitely keep that in mind as a very important part to kind of finalizing these problems. Don't forget that plus c.